so unbelievable. And I'm like, well, it's Harry Potter. I don't know.
Fluids.
It's not a question.
No, Life of Brian. I don't know. I don't know. Me and Eva were like, we have to tell everyone that we watched it.
Yep. And since your freshman year, you did an entire Patrick Swayze marathon, you don't have to do a Kurt Russell.
That wasn't me. That was
Thing
thing one and
Dana.
two.
My uncle and cousin were probably like 30 minutes.
If you haven't seen Dingo and Cat, you have to watch that.
That's
That's my biggest problem.
Alrighty. We have an unknown substance that we're putting into fluid,
Unknown substance. It's kind of scary.
unknown material. Trying to figure out what it is. Object is suspended from a scale, some sort of submerges in water. The scale reads 129.4 newtons. Originally, the material was 140 newtons. Find the specific gravity of the object and determine whether the substance could be any of these listed. Okay, so you have two regimes here. You have the object in air, so its weight in the air is the 142 newtons.
You think we have S on?
Then you have the weight of the same object in water.
Thank you.
Okay, so the first thing we want to do is figure out what the buoyant force is. So there's a couple ways you can set this up. One of the ways is you can say, well, weight in the air minus buoyant force equals water.
Be a fire camp.
Solve for the buoyant force, and you're going to get the weight in the air minus the weight in the water. So that'll be 142 newtons minus 129. 4 newtons. 12.6 newtons. I am happy to know that if I ever just randomly play this, always look on the bright side of life, you'll be traumatized.
We were dancing. Me and Eva were dancing to the end of the Always look on the bright side.
Yep.
Yeah, that I could have spent my Friday night doing anything else. But that's what I chose.
No.
That is what I chose to do.
This street.
That's like my game. Exactly. Did you find food? A snack.
Yes.
Now-
On standby.
We start by saying density of the water, volume of water gravity, density of the object, volume of object gravity. And since it's completely just submerged, okay,
Always look on.
we're also going to take into account a couple of other things. So
Gangster peanut.
no, it's the burnt peanut.
Oh, he got gangster.
We know that this, and then rho times volume, the mass of the water times gravity. That's gonna equal our buoyant force. So let's look at a ratio here.
Oh, you do? But you know that. She's right in there.
You have rho of the density of the object over density of the water.
You know that.
So this is directly from the specific gravity equation. Now, density. Mass over volume. Split mass over volume. Okay, so then I'm going to multiply by G over G. Okay, which tells us the mass of the object times gravity is the weight of the object. Mass of the water times G, the buoyant force. So, when the specific gravity equation ends up equaling the weight over the buoyant force, we're going to put in our numbers. So your specific gravity is 11.3. Okay, because remember, specific gravity is the density of whatever your material is over the density of water. So we're working everything to get to there. Now, how do we figure out the density of the material? Well, density of the object is going to be the density of the water times the specific gravity. And what is the density of water? This time, for this chapter, we're using 1,000 kilograms per cubic meter. The specific gravity is 11.3. So we get a density of 11,100 kilograms per cubic meter, which makes this material lead.
Lead.
Mhm.
PB. PB.
So if you go back to the textbook and you look at the specific gravity equation, a lot of this starts to make more sense. Okay? Remember we talked about specific gravity was at a certain temperature Celsius because that's where the density of water is a maximum, and so all that fun stuff. Okay. Let's say we have the average density of the human body at 980 kilograms per cubic meter. What fraction of the body floats above water in a freshwater pond? And what fraction floats above seawater? Specific gravity of seawater is 1.025. Okay. Water. So. So we're gonna go back to our definition where we have our volumes to our density ratios. So we're gonna have the volume of the water over the volume of the body. Rho of the body over the rho of the water. This is fresh water, so we use 1,000.
I feel so bad about reading.
You're going to get
No.
the number 0.98. Now, based off that ratio of volume of water over to the volume of the body, this is a fraction. Is this submerged or what's above the water?
What's submerged?
What's submerged? Now, how do we figure out the fraction of the water, the body above the water?
So.
So 2% of the body is above water.
It's not like you want to eat before that kid, you're just gonna puke it all out. Oh, yeah.
Yeah. Going off this model, once again, we're going to need
And they stop making it.
but we're going to need that density of the water. How do you think we find that? We have a specific gravity. Now, how do you think we work with the specific gravity of the seawater? We'll use SW instead of W. Density of the seawater over what? Yeah, specific gravity is everything compared to normal water. So that's going to be now we have the density of the seawater. All right, so the fraction submerged, density of the body, over the density of seawater, and we are going to get 0.956. So that's the amount of the body that's submerged in the salt water.
Sorry. Like, this is exactly what I'm making. Right, honestly, half my plate will be stuffing. She actually goes, I'm thinking of this.
So you have 4.4% submersion in the salt water versus 2% for regular water. This is why people take trips to the Dead Sea.
So you can float.
Yeah.
See somebody trying to get
Form of
something.
therapy, you can float in the salt, it's the saltiest water.
So salt, yeah.
Do they have salt pods?
It's a 9.
For what?
6.
So you can just float in water. It's like
Oh.
athlete recovery. We don't have them here. You're not the money, but
You should ask that we get them here.
I think I'd fall asleep.
Okay, so that's specific gravity. You figure out a lot with your ratios and specific gravity. Now let's talk about fluid flow. A couple of different flows that are important to realize. First off, a laminar flow, where everything is in a nice neat layer and everything's moving the same direction at the same velocity.
Remember it's back.
I said.
It's back.
You could also have a turbulent flow. Inside of a turbulent flow, the reason it's drawn like this is because, yes, you're getting a lot of little vortexes all over the place.
About turbulence. This week when we're flying, that was probably the worst turbulence I've ever experienced in my life.
You guys already done with that?
Yeah, we lost.
Oh,
I gotta bring that back up, Everett.
He does not give up flying.
I missed it. So when we're actually deriving things for fluids, we're looking at dealing with an ideal fluid. Incompressible, laminar flow, no viscosity. Things get a lot more complicated when you're deriving for a turbulent flow system with viscosity. Okay, the continuity equation. So first off, I mean, you can just go with A1 B1 equals A2 B2. What do you think those stand for? Not acceleration. Area. So now we're getting into a concept we call flux. So you're looking at an amount of water flow through a surface area. We call that flux. And so as you notice here, you have a pipe that starts off smaller, gets bigger. And so your area 1 times the velocity across area 1 is going to equal area 2 across with the velocity across area 2. Because the same amount of water has to cross both of them in the same amount of time. Okay, so the first thing we can say is in a certain amount of time, delta T, we're taking a certain mass of water. We subject that mass of water to kinematics. And then we say that the mass through the cross-sectional area. So we now have ideas for what delta X will look like. But we need to think about the mass crossing each individual area. So delta M is going to equal what? It equals something with density. What's it going to equal?
Is it times that area?
Well, what's the definition of density?
That's our volume.
Mass over volume. So the
DMV.
mass will equal what?
DMV triangle.
Times density.
Yeah. I don't even know what you're talking about.
The DMV triangle, that's how we learned how to do density in my chemistry class in high school.
Okay.
She showed us the DMV triangle, so it's DMV.
For me as an adult, the DMV triangles, I go to get a new driver's license.
I gotta go get a
and
new driver's
it's,
license.
You've come to the wrong window, go to that one. You come to the wrong window, go to that one. You need to go back to the first window.
My mom's
DMV
coming with
triangle.
me.
You know? Now you can get.
Now, delta V,
Mommy's coming.
what can we replace delta V with?
Did you do these?
How do we expand that out?
Gotta really look for the information point to change. Oh, into the area of it.
So it's the area times the length of that cylinder. So remember, these are like little cylinders. You have the surface area at one end times the length of that cylinder. And then, so we found delta X1.
Every time I try to go do an A, it's turning into a triangle.
Now,
Wait, go back up.
Sorry.
I'm behind. Is that the commercial?
A2 may be a larger area, but we also know if we worked it out, we would end up with the same thing.
Who's never, who's serving?
And we said that the same amount of water has to cross both of them. So that means that delta M1 equals delta M2. So then we'll say rho A1 V1 delta T equals rho A2 V2 delta T. And when we divide out rho and delta T, we get A1 V1 equals A2 V2. So we end up at the continuity equation. You also have these two equations that you can use to solve problems. Mass flow rate of a fluid, delta M over delta T is rho AV. Volume flow rate of a fluid, delta V over delta T equals A times V. So these are also very helpful in problem solving. Okay. Garden hose fills a 32-liter bucket in 120 seconds. The opening at the end of the hose has a radius of 1 centimeter. How fast is the water traveling as it leaves the hose? And B, how fast does the water travel if half the exit area is obstructed by placing your finger over the opening? We've all done that in the summer. It needs to go a little faster, doesn't it? Okay, so the first thing we're going to want to look at is, so we're looking for a speed. So we want things in meters per second. So liters isn't going to cover it. So we know that 1 liter.
Yeah.
So that means that 32 liters
You're just talking about.
is 0.032 cubic meters. Now, we have cubic meters and seconds. What equation do you think we can use to solve this? Cubic meters is a what? Liters is a what? Not metric. Liters is a what? Volume. And then seconds is what? And we're looking for a velocity.
DMV triangle.
Nope.
Don't worry, Piper, you'll get it one of
We
these
can
times.
Volume flow rate. Okay, so
Temperature gland.
okay, so then we solve, that's going to be V for velocity, change in volume. It needs to be a lowercase b, one's uppercase, and over A delta T. Change in volume, so A becomes what? Well, look, we have radius of 1 centimeter. A becomes what? The surface, that surface area, it's a cylinder, it's a circle, so what is A? Pi r squared. Here we go. The velocity. Let's see.
I got yogurt.
Okay, so down here we're going to 0.01 meters.
I don't have the aqueduct. Because it's like the fluid. So like.
120 seconds.
That's that. It's your fourth metric.
Your volume. Meters, you end up with 0.85 meters per second. So that's the hard part. Part B you do just by saying that Your velocity is gonna be delta V over 1/2 pi r squared delta t.
That's what I always forget.
So essentially, it's gonna be your 0.85 times 2. You see that? So the 1/2, if we just flip here, 2 delta V pi r squared delta t. You take your 0.85 times 2, and then you have part B.
The first.
So see, so far, the solutions in this chapter are not that bad. Is fluid moving up to what you hope for?
I guess.
It's not as exciting as you think it's gonna be. Now, a lot of the stuff we're solving now, and especially what we're gonna be going with Bernoulli's equation. So between Bernoulli and viscosity, you start getting into a lot of your biomedical stuff. Like, for example, you start to realize that blood pressure has nothing to do with the cross-sectional area of the blood vessel. It has to do with something else, because pressure in fluids has to do with depth. Less fluid, less depth, less pressure. But you know that pressure goes up, so you figure out why. Okay. Now, this fun thing at the top here, this is Bernoulli's equation. Pressure 1 plus rho gy1, so the density of your solution, gravity. And so this is analogous to your gravitational potential energy, plus 1/2 rho v1 squared, equals pressure 2 plus rho gy2 plus 1/2 rho velocity 2 squared. So it's kind of like a big long equation where a lot of things will equal 0, and you can figure out what you need to solve for. So one of the ideas we're going to need that's just going to equal volume. We start to get this with the fact that fluid is incompressible. Now, if we take this figure down here, at A1, let's see, acceleration increases, so positive work is done. At surface 2, acceleration is going to decrease. So, why do you think that is? So negative work done as acceleration decreases. Why do you think acceleration increases at the left side? Look at the pipe, what's happening to it? Getting smaller. So you want that same volume to cross the same area. As it gets smaller, velocity is to increase. And since area is getting bigger on the other side, you don't want it going as fast, or a larger volume will cross in the same amount of time. So that has to decelerate. Okay, so the total work done on the water in this system, and then of course this first one here is to show you the difference between like Y1 and Y2. Okay, so the total work done is going to be the force A1 delta X1 minus the force at A2 delta X2. So that's P, so the force is P1 A1, because back in the beginning parts of the chapter, force is pressure times area. Okay? And A times delta X is V. A 2 times delta X2 is also V, so we end up with P1 minus P2 times volume. So then what do we also remember? Remember this? Total work is delta K plus delta U. So in this case, there's the potential is again only the gravitational potential as you're either going up in a pipe system or down. We're not looking at elastic potentials in this case. Now, later on, when you get more advanced, blood vessels are elastic, so you may actually bring in some elastic potential, but you know, we'll save that for your medical school.
Thank you.
So work,
I'm not going to med school.
those of you going on to any kind of graduate school in biology or chemistry, you would definitely deal with that. Gonna have to brush your calculus off.
But this can be-
Now,
I've been talking
remember this is 1/2 n v2 squared times 1/2 n v1 squared
I love electricity.
plus
My dog.
mgy2 minus mgy1. And mass, what again, what does mass equal? Density times what? Volume. So we're gonna get 1/2 rho v v2 squared, 1/2 rho v v1 squared plus rho v y2 minus rho vg1.
These are cute.
And that's going to give us 1/2 rho e v2 squared minus v1 squared. So this is another way to write Bernoulli's equation. So a lot of the way we were doing the work energy theorem, now you're just dealing with fluids. And you have all of these different things, kinetic energies and potential energies, and you're like, which one's going to zero? And you'll see in problem solving, this form of the equation is really quite helpful because we get that P1 minus P2, which you remember what P1 minus P2 is called?
The B, what?
Delta P, which is the,
Change in pressure.
it's a specific kind of pressure. What if I told you that delta P equals rho delta P is called the what? Gauge pressure. Okay. So let's say water flows for. You guys okay out there?
I do too, but I can't.
Did everyone put their name on that piece of paper? Did it make it all the way around? Okay, good. I'll pick it up at the end. Water flows horizontally through a garden hose of radius 1 centimeter at a speed of 1.4 meters per second. The water shoots horizontally out of a nozzle of radius 0.25 centimeters. What is the gauge pressure of the water inside the hose?
Oh my God, this matches the light of legends.
Well, we start by saying And how can you instantly make this easier?
Cancel some stuff out. Like the-
One entire part becomes zero. What? Garden
You
hose.
asked mine, she just did.
Garden hose.
So.
Garden hose. Straight out. It doesn't, there's no change in altitude, so your potential energy goes to zero.
Yeah.
Then, what else can cancel out?
Half the time.
The volume.
Okay, now however, we are going to need a V2. We have a V1, but we need to know what V2 is as the water exits the hose. Okay, so we have V1. Well, we can find V2 by using
He went home.
okay, so we can solve for V2.
I just hate that.
So V2 is going to be 22.4 meters per second. So now we can we have all the numbers we need to solve for the gauge pressure. What is the density of water that we've been using?
Well, see, I said I was gonna do that too, but I told myself.
The gauge pressure ends up being about 900 pascals or about 25 kilopascals. So that's a quick way to use Bernoulli. Anyone taking standardized exams, you're going to want to remember Bernoulli.
Bernoulli?
Mhm.
Dessert. Sorry, I'm just saying.
Another thing you're going to want to remember is viscosity. So, internal friction of a fluid resisting the flow of the fluid. So best of luck. That's a French name. I hate any of you who had me in chemistry. I hate French names. It's like Poisson equation. I can't. Like, you know, we are going to say half the letters in the word. I can't. Okay, so again, you have your volume rate of flow, your delta V over delta T. It's going to be pi over A. Delta P over L. So delta P is of course the pressure difference between the ends of the pipe. L is the length of the pipe. R is your inner radius of your pipe, and eta is a number unique to the fluid, and that's the fluid's viscosity. Now, if we're looking at you remember that we have a velocity. We're just going to call it average velocity equals over A, your volume rate of flow divided by the area of the cross-sectional area of the tube. Since this is a viscous fluid, we can only get an average velocity of the fluid inside the tube. It will change differential to differential, but we can get an average velocity inside the tube.
exactly does the Q mean?
The Q, oh, that's your delta V over delta T. The Q equals delta V over delta T, or your volume rate of flow. The book uses Q. I don't like that because we're going to be using Q for something different next semester.
Don't worry, we won't remember.
What do you think of?
That's what I'm afraid of.
Anybody?
Let's try to muscle through this problem. The town water supply is operating at nearly full capacity. The town board decides to replace the water main with a bigger one to increase capacity. If the maximum flow rate is to increase by a factor of 4, what factor should the radius of the water main be increased to? Okay, so we want a ratio of volumes. Okay, so I can say, I'm going to do my new volume over delta T, volume over delta T to get a ratio. I delta P 2 to the 4th. L over I delta P to R1 to the 4th. 8 L. So it's the same fluid. So we're kind of looking at, all we're thinking about is changing the radius. Same fluid, same kind of pipe, just different radius. Okay, well, the delta T is going to cross out. Your 8L goes away. Your pi delta P goes away. The ratio you end up with okay, so we end up here. Now, the maximum flow needs to increase by 4.0. So we need an increase to the volume through the pipe of 4 times what it was. So your delta V, delta V2 over delta V1, what we're going to end up with here is R2 over R1 to the 4th equals 4.0. That delta V ratio needs to be that 4.0. Okay, so then your R2 over R1. How do I get rid of that 4 there? Well, what will I do to the right-hand side?
Take it to the 4th power.
Yeah, the 1/4 power or the what root? Yeah, the 4th root. When we do that, we get 1.41. So radius 2 needs to be 1.41 times radius 1. So the new radius needs to be 1.41 times larger than the old radius. This is an excellent engineering problem. Okay, so there's some important topics for future standardized exams. In particular, your standardized exams, like I would know your continuity equation, I would know Bernoulli, I would know viscosity. Especially start thinking about if you're ever dealing with blood flow, viscosity is going to become a big thing. Blood is extremely viscous. Trying to figure out why blood pressure increases when, I mean, even though blood vessels decrease in radius, that's not what causes the pressure increase, because less fluid means less pressure from the fluid. So what increases the pressure? It has to be a factor of the what?
The velocity.
The velocity of the blood. Okay, so that's the end of fluids. When we come back, we'll work on sound.